mevalonate? Well, we know that we had 2 acetyl-CoA to start with, and we added in 1 more acetyl-CoA to make HMG-CoA. Each acetyl-CoA has 2 carbons, so mevalonate is a C6 compound. This is also the end of stage 1, so we'll make a little line right here. End of stage 1. Alright? Stage 2 is nice and simple. All we're going to do, stage 2, we're going to have one reaction that's going to change this mevalonate into an activated isoprene. Why is it activated? It needs to be activated so that it can form a bond. You cannot create bonds without the input of energy. This is where the energy is going to be input. So what's going to happen is you're going to have, I don't think this was well stated in the notes, you're going to have ATP. You're going to take the equivalent of 2 ATP. You're going to attach 2 phosphate groups onto this isoprene. At the same time, you're also going to be losing a carbon dioxide. That means that this isoprene is actually a C5 compound. All right? Excellent. So that is the end of stage 2. Stage 3 will come in 1 second. I'm going to clear this off and we'll keep moving. Stage 3 is fairly simple. Also, we don't have a name for the enzyme that does stage 2. We do know that it is ATP dependent and that it releases CO2, but we don't have a specific enzymatic name. Stages 1, you would need to know the enzyme names. Beyond that, it's all just kind of understanding how cholesterol kind of is pieced together. So in stage 3, we have these isoprene subunits, which are activated. Each P here is the same thing as saying O- bonded to P, bam. Something like that. This O would then go to the R group, or the isoprene group in this case. We know that isoprene is a C5 compound, and what we're going to make from this isoprene in stage 3 is we're going to make squalene. Squalene is a C30 compound. There are 30 carbons in squalene, which means we need 6 isoprenes, activated isoprene compounds to make squalene. Anything else in stage 3? Not particularly. So that is the end of stage 3. In stage 4, squalene is going to form cholesterol. A couple things to remember about this step. Cholesterol is C27, which means we're going to be losing 3 CO2s. During that processing step. Within stage 4, there are 23 enzymatic reactions. 23 enzymatic reactions that actually convert squalene into cholesterol via some oxidations, some removal or migration of methyl groups, and some hydroxylations as well. So that is essentially the entirety of cholesterol synthesis, which actually isn't too bad. Some of the cholesterol products, again, were the steroid hormones, vitamin D, and alright, let's do a little bit of math here. So we're going to come back to how many isoprenoids you actually need to create cholesterol. So for cholesterol, we know that cholesterol was a C27 compound. This is cholesterol. It was made from the C30 compound squalene by the C5 compound, and that is the activated isoprene. Isoprene was made from the C6 compound mevalonate, and each mevalonate was made by a C2 compound acetyl-CoA. So let's work this backwards just a little bit. To get from cholesterol to squalene, we don't need to add on any carbons. It's a 1-to-1 ratio. However, to get to 30 from our 5 isoprenes, we're going to need 6 of them. 6 by 5 equaling 30. In order to get 6 isoprenes from mevalonate, you're going to need 6 mevalonates, as you're going to release a CO2 and add on those 2 phosphate groups. In order to get 6 mevalonates from acetyl-CoA, you need 3 acetyl-CoA per mevalonate. 3 by 6 is going to be 18 acetyl-CoA. These acetyl-CoA are going to need to be transported across the plasma membrane of the mitochondria. In that transport, it's going to require at least 18 ATP just to transport the acetyl-CoA. If we don't have NADPH from the pentose phosphate pathway, this number is going to go up a lot. We don't actually know what that number is right now, so I don't believe Van Fleet would ask us any kinds of questions on that specifically. That's about it. So we know that we use ATP to transport the acetyl-CoA. We also know that we use the ATP here. So we need 2 ATP per isoprene unit. ATP to AMP is the equivalent of 2 ATPs. So we know that each time we go here requires 2 ATP. That's going to happen 6 times, so we've got 12 ATP used. So in order to make 1 cholesterol molecule, we're going to need to use at least 30 ATP. And that's less any of the energy that would normally be created by that acetyl-CoA as it passes through the citric acid cycle. That's it for today. Have yourselves an awesome evening.